So it means if you have a bigger diameter or bigger system, so you can put more poles. So the limitation is that if you have a small space, so it is impossible to wound more poles here. The advantage of more poles means that you have the rotation of your machines. You can limit to a lower speed to produce the 50 Hz or 60 Hz output of AC source to the terminal. So means that you have higher inertia of system. You turn the shaft and the rotor. Then if you put more poles, so the rotation you need to turn the rotor is much lesser compared to high the lesser poles which require higher speed to produce the same frequency of terminal voltage to the grid. Okay, we have a Salem pole rotor generator, and this is the construction of the Salem pole. And you have stator coil here. At the stator parts, we have rotor coil wound to the extruded or protruded poles in the rotor parts. This is construction of 4-pole Salem pole. This is the image of the 6-pole Salem pole generator. Okay, meanwhile the non-Salem pole rotor generator means that the rotor or cylindrical type kind of construction in terms of the rotor. So magnetic pole with windings will be embedded with the surface of the rotor. Windings here. So electromagnetic windings embedded in the notches of the surface of the rotor, normally in kind of 2 or 4 poles construction, and will be embedded on the surface. Most of it will be on the surface. So it's just like a wound rotor motor. And so this is for 2 poles we have here, and it will comes into here and come out to here, so it wounds accordingly. So this is the 4 and 2 pole Salem pole. This is 4 poles, this is 2 poles. So this is construction or the figure of the Rund rotor generator, sometimes called turbo generators. So this is a 2-pole non-Salem pole type of rotor. This is 4-pole non-Salem pole generator. So what are the difference between the Salem and non-Salem poles? So we have, for the Salem pole, the rotor has a larger number of projecting Salem poles with their coils bolted on the rotor, on the shaft. Meanwhile, your non-Salem pole, the rotor consists of no smooth solid force steel cylinder. We have no slots and for accommodating field coils. The Salem pole machine usually are built in larger diameters, but in small axial lengths. Means that it will be such a thin motor or generator. Meanwhile, you have for the non-Salem pole, they are small diameter and just like a pencil type, which their diameter is small, but the length is quite long. Usually the number of poles on the rotor is 4 or more. Minimum is 4 and can exceed up to few more poles, but limited with the construction of the machine or the generator itself. So more poles means that you have to put more coils and more space you require. And in terms of non-Salem pole, usually the number of poles on the rotor is 2 or 4 only, and it will speed at a higher speed compared to Salem pole. The Salem pole rotor creates considerable air turbulence because we have the protruded poles, so it creates air turbulence inside the gap. So we have a relatively high windage loss, kind of silent pole kind of machine. Meanwhile, in the windage loss in terms of non-silent pole, the losses will be quite low, and the energy loss by the moving of the air around the gap between the rotor and the stator will be less compared to the silent pole. So the speed of the shaft we need in kind of 120 up to 500 rpm only. So this is considered as medium speed. Meanwhile, non-silent pole usually we use or we apply in the rotation kind of 1000 to 3000 rpm rotational per minute. So in terms of power rating, this one usually being used in hydro power kind of machine or generator, can produce up to 800 megawatt, and so it's considered as low power generation machines compared to higher power generation, which can reach up to 1500 megawatt turbine, usually used inside our wind turbine, gas turbine, and so we use non-silent pole kind of machines or generator. Silent pole usually be used in hydro kind of turbine, hydro, the old wind turbine, windmill turbine, and like what we have in the Dutch country. So this is the silent pole compared to the non-silent pole. And also in terms of their construction, the poles are sticking out from the surface. So the in terms of your non-silent pole, the unslotted portion of the cylinder acts as your poles. So the winding will be concentrated on the poles and uniform air gap. But non-silent pole, the windings are distributed and essentially uniform air gap. The mechanical weakness of the silent pole is more prominent compared to non-silent. So we use in the water turbine as the prime mover. Meanwhile, your non-silent pole will be constructed in kind of in factory base. This one is manual base, this one factory base. So it will be mechanically stronger compared to non-silent silent pole. The prime mover use steam turbine, usually used in steam turbines or electric motors. So the poles for sure it will be sticking out from the space. This is unslotted portion, cylindrical, which acts as the poles. So the principal operation, the DC will be constructed or touched to the rotation parts of the generator. Okay, the DC excitation current, field current, IF in the rotor generates a flux. So it refers to your coils here. Coils here will be your fields which connects to DC source. So positive, negative. So it will produce your electromagnetic fields. And at the same time, when it rotates, so you are producing a rotating magnetic fields and rotating magnetic fields. So we have DC excitation current which flows inside your fields, flows into the fields. So at the same time it rotates, and it rotates clockwise, and the turbine, by the turbine, it will drive the rotor and producing a rotating flux. And the rotation causes the flux change in the armature or the stator windings. So you have a flux change here, and the rotating flux induces AC phase in the stator winding. It produces alternatingly current, positive then negative, positive negative. So it produces AC to the terminals. So the rotating flux induces AC phase voltage in the stator windings. E equal to N d pi over dt, or E equal to C N pi here. So this rotor induced voltage in the stator. So this is your stator, and your stator here. It produces voltage alternately, and so it produces positive, negative, and this positive, negative will be filled by your terminal here, and the terminal will fill or will induce this positive and negative and internal generated voltage here to the grid. So you can click to the link here to see how synchronous generator works, or how to appreciate this sequence of operation or steps of how the synchronous generator works. So you take some time and you watch here, and you come back to the slide.
It is capable to generate AC power at a specified frequency. It is also called a synchronous generator. Electricity is produced in alternators by electromagnetic induction. To generate electricity in a coil, either the coil should rotate with respect to magnetic fields, or a magnetic field should rotate with respect to the coil. In the case of alternator, the latter approach is used. Rotor and armature coils are the two main parts of an alternator. Rotor produces a rotating magnetic flux. Armature coils are stationary. And rotating magnetic flux associated with the rotor induces electricity in the armature coil. This kind of rotor shown here is known as salient pole rotor. For gaining better insight of its working, let's consider a rotor with just 4 poles. Rotor coils are excited with a DC power source. Magnetic field produced around it would be as shown. The rotor is made to rotate by a prime mover. This makes the rotor flux also rotate along with it at the same speed. Such revolving magnetic flux now intersects armature coil, which is fitted around the rotor. This will generate an alternating EMF across the winding. Here is a slowed-down version of rotor-stator interaction. For this 4-pole system, when the rotor turns half revolution, induced EMF takes 1 complete cycle. It can be easily established that frequency of induced EMF, rotor speed, and number of poles are connected through following relationship. It is clear that frequency of electricity produced is synchronized with mechanical rotational speed. For producing 3-phase AC current, 2 more such armature coils, which are in 120-degree phase difference with the first, is put in the stator winding. Generally, one end of these 3 coils are star connected, and 3-phase electricity is drawn from the other end. It is clear from this equation that in order to produce 60 Hz electricity, a 4-pole rotor should run at following RPM. Such huge RPM will induce a tremendous centrifugal force on poles of the rotor, and it may fail mechanically over time. So salient pole rotors are generally having 10 to 20 poles, which demands lower RPM. Or salient pole rotors are used when the prime mover rotates at relatively lower RPM.